And the example is find the critical numbers of the function f of xy, which is equal to x squared plus 4xy minus y squared minus 8x minus 6y. Okay, what do we want? We want partial x being partial x being 0 and partial f partial y, maybe like this is better, being equal to 0. So I need to solve this system of equations, okay? Partial f partial x is equal to 2x plus 4y minus 8. 2x, derivative of 4xy is 4y minus 8. Partial f partial y is 4x minus 2y minus 6. And I want these to be equal to 0. Okay, so excuse me. What can I do? I'll divide the first equation by 2 to get x plus 2y minus 4 is equal to 0. And then I can do the same thing for the second one in order to simplify it. But I can see that here I have 2y, here I have negative 2y. So I will try to solve this system of equations in two variables. This is very simple, right? You have done this in high school by elimination, right? So if I add these two equations, I'll get 5x, 2y minus 2y is 0, minus 10 is equal to 0, or from here x is equal to 2. That is obvious, right? And once you have x, again, this is a linear equation here, plug it in any of these two equations and you'll get 1 y. So y is going to be, from this equation here, 2 plus 2y minus 4 is equal to 0, 2y is equal to 2, and hence y is equal to 1. So here we have the critical one critical number at the point 2, 1. Okay, any questions? And then if you look at the graph of this function, it's plotted right here, right here. So is this so this is the graph of the function that we have. Whoa, trying to, this is not working right now. Okay, I cannot really point the points here because it doesn't produce a good enough graph. Anyhow, okay, so that's how we find the critical numbers. Okay, so these critical numbers, similarly like in Cal 1, it may not give us the points where we have extreme values, right? So nothing guarantees that I will have either maximum or minimum at these points. Okay, let's do another example. The example is the same. Find the critical numbers of the function f of xy is equal to x plus y e to power negative xy, okay? And I'll give you, let's say 5 minutes for you to find the critical values by yourself if you can. Okay, so I want the gradient of f to be the 0 vector, right? Okay, so that means partial f partial x, derivative of x is 1, so e to power negative xy by the chain rule plus the derivative of e to power negative xy times x plus y. The derivative of e to power negative xy is e to power negative xy times the derivative of negative xy, and that's negative with respect to x, negative y. Here by symmetry, this derivative is negative xy minus x plus y e to power negative xy. And I want to solve the system of equations. Of course, this is not going to be a linear equation, this to be equal to 0. Okay, so let's see how are we going to do that. Well, in both cases, first, you can factor e to power negative xy for this term here, and you get 1 minus y x plus y is equal to 0. And the same thing can happen for the second equation, 1 minus x plus y is equal to 0. Now, the function of e to power negative xy will never be 0, right? This factor here cannot be 0 for any xy. Okay, even if one of them is 0, if both of them are 0, e to power 0 is 1. So this can never be 0, which means that I can divide both equations by this expression. Okay, because again, it will never be 0. That leaves me with the system of equation 1 minus yx minus y squared is 0, and 1 minus x squared minus yx is equal to 0 by dropping the parentheses. Okay, or from here we get that 1 is equal to y squared plus xy, right? And here I get 1 is equal to x squared plus xy. Okay, well, if these two equations are equal to constant 1, that means y squared plus xy has to be equal to x squared plus xy. Right? 1 is equal to y squared plus xy, and here 1 is equal to x squared plus xy. That means this is equal to 1 and this is equal to 1. Well, those two have to be equal. So put them equal here to each other, and then I have this product is the same. So finally I get that y squared is equal to x squared. Okay? Taking square roots on both sides, I get that x is equal to plus or minus y. Okay? So at this point, I just have a relation between x and y. I don't have a constant, a value for neither x nor y. but I can come back here, wherever you want, right? I can come back here and taking that x is equal to y, this equation becomes 1 is equal to x squared plus x times x, y is x now, x squared, which means this is 2x, x squared, x is equal to positive or negative square root of 1/2, or x is equal to positive or negative 1 over square root of 2. So what do I get here? When x is equal to y, I get the point, well, the first one when x is positive 1 over square root of 2, then y also has to be 1 over square root of 2 because they're the same. And the second one, when x is equal to negative 1 over square root of 2, y has to be the same value, negative 1 over square root of 2. Okay, so far, what do I have? So far, I have 2 critical points. Let's see what will happen when x is equal to negative y. When x is equal to negative y, again, I plot that in here. I get 1 is equal to x squared minus x squared, and this doesn't produce anything, right? This doesn't result with any critical points because this doesn't make any sense. Okay? So again, in this, so not again, but in this problem here, in the second example, we have only two critical points. Any questions? Well, I plotted this graph, and I obtained this surface, right? And then I was able to plot the point square root of 2 over 2, which is 1 over square root of 2, 1 over square root of 2, and the z value, of course, and negative 1 over square root of 2, negative 1 over square root of 2, and the resulting z values. And that resulted in finding the point A and B, right? So look at this. I have, this point is 1 over square root of 2, 1 over square root of 2, and the z value, right? It is a critical number. For example, here, if you put, if I want to plot the plane z is equal to negative square root of 2 times e to power negative 1 over 2, okay? And then what? Where is it? Okay, that's for the point, okay. So positive right here. There you go. There is the plane going through the point A, right? And as you can see, that plane is a horizontal plane. It's a tangent plane to this level surface at the point A, and that's why the point A is a critical number. And the same thing is going to be with the point B. So if I just duplicate here and I plug a negative in front, there is going to be the plane crossing through the horizontal plane passing through B, right? And we calculated that the point B is a critical point. Okay, let's continue talking about this example right here. So as I said, a critical number, critical point doesn't mean that we have neither minimum nor maximum, right? And in Cal 1, something like that happened, for example, with the function x cubed, right? Y is equal to x cubed, the critical number is at 0, but here only the tangent line is flat, the tangent line is horizontal, but we don't have neither maximum or minimum. That situation can happen in multivariable calculus, but something that can happen here and that we haven't seen in Cal 1 is the saddle point. So look at this. In 2 dimensions, if I flatten this curve in 2 dimensions, I have obviously this level curve, right? It looks like a parabola, to which the tangent plane in 2 dimensions is just going to be this tangent line, right? So what do we have? This is going to be concave upward, and if it's concave upward at the critical point, we talk about absolute minimum, and that's obvious from this graph. But now look at this. If you rotate this a little bit and you observe the same situation from here, right? I have this level surface, sorry, this level curve right here in 2 dimensions. I do this right here. There you go. When the tangent plane is going to be horizontal, which means in 2 dimensions, flattened tangent plane is a tangent line. And at the same point here, the level curve is concave downward, which means I have maximum. So at the same point, in 3 dimensions from here, I have maximum, and at the same point here, I have a minimum, okay? This point is something new that we learn in Cal 3. This point is called a saddle point. So we're going to learn in this class that there are 3 possibilities. You can have absolute minimum or local minimum. You can have a local maximum, and you also can have a saddle point. And in this case right here, we have that situation when we have a saddle point. So in this class, I'm just going to write down the second derivative test for functions defined in 2 variables, okay? And we will discuss more about it next class. Today, I'm just going to define it, and then I'm going to try to solve an example to show you how to do it. And then we will, the nature, or I'm not going to try to prove it, but why the second derivative test works, that at the beginning is just going to be a little bit awkward. We'll see on Friday. So the second derivative test for functions in 2 variables. 1. If the second partial derivative with respect to x is negative, and this discriminant d that I'm just about to define in a second is positive, at the point A, B, we have a local maximum. Okay? 2. If the second derivative with respect to x is greater than 0, and this discriminant of the Hessian matrix that I'm about to tell you what does it stand for, it's positive, we have local minimum. So let's stop here just for a second. This discriminant being defined as f double x, f double y minus the mixed derivative squared needs to be greater than 0 in order to talk about local maximum and local minimum. Okay? And then based on the sign of the f double x, okay, we determine whether it's local maximum or local minimum. If the discriminant is less than 0, then we have a saddle point. And 4, if the discriminant is equal to 0, then the second derivative test is inconclusive. Okay? This expression here, it's called the discriminant of the Hessian matrix, and the Hessian matrix is equal to f double x, f xy, f yx, but by the Claro's theorem, these are the same, f double y. The determinant of this, matrix, it's called the discriminant denoted by D in our case. So f double x, f double y minus f of xy, because these are the same by the Claro's theorem, squared. Okay, any questions? So let's do an easy example for today, and with that we're going to finish. Example: find the local extreme values of the function f of xy is equal to xy minus x squared minus y squared minus 2x minus 2y plus 4. And just by looking at it, this is going to be some kind of paraboloid, okay? So what do we have to do? Give me a second, guys. You can please find the partial derivatives of the first and the second order, okay? And I'll be back in a second. Okay, so partial of partial x is y minus 2x minus 2. Partial f partial y is x minus 2y minus 2. First of all, I have to find the critical points. Where the first order partial derivatives have to be equal to 0. Okay, so that means that I have a system of equations: y minus 2x minus 2 is 0, and x minus 2y minus 2 is equal to 0. So from here, I don't know, y is equal to 2 plus 2x. Apply it in this equation, you get x minus 2, 2 plus 2x minus 2 is 0, x minus 4 minus 4x minus 2 is equal to 0. So I get negative 3x minus 6 is 0, or simply x is equal to negative 2. X is equal to negative 2. Once I have x, I'm gonna come back and figure out how much is y. So y is equal to 2 plus 2 times negative 2, and that's equal to also negative 2. So the critical point of this function, there's only one critical point, and that is xy is equal to negative 2, negative 2. Okay, so here we can write only one critical point, and that's xy is equal to negative 2, negative 2. At this moment, we don't know whether this point is local minimum, local maximum, or a saddle point. In order to figure that thing out, we have to apply the second derivative test, okay? And the second derivative test depends on the determinant of this Hessian matrix. So first, let's find the second order derivatives. F double x is just negative 2. F double y is just negative 2. And the mixed second order partial derivative is 1, right? How do we find that? Well, I find the derivative of partial f partial x with respect to y. These don't depend on y, so its derivative is 0. Derivative of y is just 1. Okay, so the discriminant is equal to in which case I get negative 2 times negative 2 minus 1 squared, which is 1. And this is obviously less than 0 because, greater than 0. Negative 2 times negative 2 is 4 minus 1 is greater than 0. Okay, so if you look at the second derivative test, okay, if this discriminant is greater than 0, then we have either a local minimum or a local maximum. Okay, that depends on whether the second order partial derivative with respect is either greater or less than 0 at that point. So since f double x is less than 0, right? This gives us the concavity, right? Gives us the concavity in 2 dimensions. Because it's concave upward, we have local maximum. Sorry, minimum. It's concave. It's concave downward. So we have local maximum at the point negative 2 and negative 2. Okay, any questions?
Why is it that we look, this is Charles, by the way, why is it that we look at like the second derivative with respect to x and not the one with y? Like, wouldn't it do this?
I'll talk about this in the next video. I will explain this. So let's concentrate here only on the technical point of view, because very, very short explanation. Okay, very short explanation, and I'll get into more details later on. Okay, let's come back here. Okay, if the discriminant is positive, okay, that means that I wish I could look at the discriminant right here. Okay, when do we have positive discriminant? We have positive discriminant only when fxx fyy is greater than fxy squared. Do you agree with that, Charles?
Yeah, and like fxx and fyy have to be of the same sign for it to be positive, right?
When would this be positive? This would be positive if both of them are positive or both of them are negative, right? So if fxx is negative, that means fyy is negative. If fxx is double x is positive, f double y is positive. So we just evaluate one. This definition here would have been absolutely the same if you say fyy.
Okay, that's what I thought. Okay.
You have to look at one. That's what I'm saying. But I'm going to go into more details next class. But this is the idea, because if we're talking about local maximum or local minimum, the discriminant has to be positive. In order for the discriminant to be positive, this product has to be greater than the square of the mixed partial derivative. And this is positive if either both of them are positive or both of them are negative. So that means all I have to do is evaluate one to know how much is the, all I have to do is just evaluate one. Okay?
Great, thanks.
So I'll do one more example and then we're gonna be done for today. I'm gonna go somewhere to, I don't know, some of the final exams. Hopefully I'm not going to regret about this one. So there you go, final 2015. It says find and classify the critical points of the function 3xy minus x squared y minus xy squared. Okay, so basically find the local extrema of this function if there is a local extrema. Okay, so let's find partial x is 3y minus 2xy minus y squared, and partial y is 3x minus x squared minus 2xy. Okay, and these have to be equal to 0. So from here, I can express how much x is, right? One way to solve the system of equations, right? It's not linear, it's not going to be easy. But from here, I can express at least how much is x. So I have 3y minus y squared is equal to 2xy, right? Just bringing this side on this side of the equation. And then dividing both sides by y, you get 3y minus y squared over 2y is equal to x. Right? By taking the fact that y is different than 0, so I can cancel. If y is different than 0, then x can be simplified to the point of x is equal to 3 minus y over 2. Right? Because you factor y from here, you get 3 minus y over 2. Okay, now if you have x, plug it in this equation, and let's solve for x. So let's solve for y. So you have 3 times, now x is 3 minus y over 2 minus 3 minus y squared over 2 squared minus 2 times 3 minus y over 2 times y is equal to 0. So let's bring everything under common denominator of 4. So we have 6, 3 minus y. Just please stop me at any moment, right? So the common denominator of 4, this is 2. So I multiply this expression by 2, 3 times x minus y, minus 3 minus y squared, minus 2y, 3 minus y is equal to 0. Multiply both sides by 4, multiply both sides by 4 to get rid of the denominator, and factor out the factor 3 minus y. We're left with 6 minus 3 minus y from here, minus 2y is equal to 0.
For the last factor on the right, shouldn't it be like minus 4y?
This one here?
Yeah.
It should be 4y. Thank you very much. Okay. And then this is 3 minus y times 6 minus 3 is 3. This is positive y minus 4y minus 3y is equal to 0, right? Can you check my solution, please?
That works.
Looks good?
Yeah.
6 minus 3 is 3. This is positive y minus 4y minus 3. Okay, so finally from here, I get my two y's, right? Y is 3 and y is equal to 1. This implies that if you plug it in here, 3 minus 3 is 0 for x. And this implies that x is equal to 3 minus 1 is 2 over 2 is 1. Okay, so I have two critical numbers. Zero, 3, and 1, 1. Okay, any questions? No. Okay. Now, we have to be careful about one thing, and that's the following thing. Here I said that y is different than 0. Here I said that y is different than 0, so I can cancel this one by y. But what will happen if y is equal to 0? So we continue looking for these critical numbers. If y is equal to 0, then the partial derivatives become what? If y is equal to 0, I get 0, 0, 0, so 0 is equal to 0. And partial f partial y becomes 3x minus x squared minus 0 is equal to 0, right? So be careful. You have to account for every value. So I was able to simplify this expression as long as y was different than 0. But now you have to ask the question, what happens if y is equal to 0? Because as you can see, the domain of this function are all the real numbers, all the points in R2. When y is equal to 0, partial f partial y becomes x. 3 minus x is equal to 0, which gives us 2 points. X is equal to 0 and x is equal to 3. Which produces what? Produces two more critical numbers, 0, 0 and 3, 0, plus two more critical numbers. As we said, 3 and y 0, so 3, 0, and 0, 0. Any questions? Okay. Finally, we just have to use the second derivative test. So let's find the second order partial derivative. F double x is just negative 2y, right? Fxy is 3 minus 2x, 3 minus 2x minus 2y. And f double y is just negative 2x. Then the discriminant is fxx fyy minus fxy squared, which is equal to negative 2y, negative 2x minus 3 minus 2x minus 2y, which is equal to 4xy, and this is squared, sorry, minus 3 minus 2x minus 2y squared. And I'm not going to expand this one because that's a little bit too much work. What do I have to do? Now I have to determine the determinant, figure out what's the value of the determinant at these 4 points, at 0, 0, at 0, 3, at 1, 1, and at 3, 0. So how much is going to be the discriminant? Here, the discriminant is going to be a negative 9 at 0, 0, right? This is 0, this is 0, this is 0. 3 squared is 9. With negative in front, I get negative 9. Negative 9 being equal to, being less than 0, I have a saddle point. Okay? If the discriminant is negative, we have a saddle point. At the point 0, 3, so this is x is 0, so I have 0. This is also 0. So I have 3 minus 6 is negative 3, squared is 9 with negative in front, again negative 9, less than 0, saddle point. Let's look at the last one. Y is 0, so this is 0. 2 times 0 is 0. 2 times 3 is 6. 3 minus 6, negative 3, squared is 9, with negative in front, negative 9, less than 0, saddle point. And the last one, it's 1, 1, in which case I get 4 minus 3 minus 2 minus 2, that's 3 minus 4. 3 minus 4 is negative 1, squared is 1, minus 1, which is equal to 3, which is greater than 0. So here I have either min or max, and I have to figure that one out. And that will depend on f double x evaluated at 1, 1. F double x evaluated at 1, 1 is negative 2, which is less than 0. So we have a local, because it's less than 0, is concave down, a local maximum. And that's about it for today. So this is the material, the whole material for the test next Friday. Okay, more explanation is going to come on Friday, and more examples are going to come on Friday. And then on Monday, I will do a big review of the whole material for the test. And then if there are no questions next Wednesday, I'll start with double integrals. If there are questions, I'm gonna continue doing the review. Any questions for now?
Ivo, since for the second assignment, like when I sent the assignment, like it wasn't as a PDF file. Do you want me to resend the pictures as a PDF file?
No, not the assignment. I want you to learn, if you don't know yet, how to upload your test in PDF file on Leah Dropbox. What is done is done. I thought that I'm not going to have problem, and then when I saw what I have to deal with, I underestimated myself and my time available and the whole situation around. So don't worry about that one. I will figure that one out. Okay, Chris says that, or you can all read this. Cam Scanner. You guys know these apps. I don't, guys. You are from this time. I feel like I was born in 1890s. So for the test, and one file, okay, one file. Don't make me compile your PDF files into one file. Obviously, the solutions are going to be very big. Look at this problem, right? It requires a lot of solutions. Bravo, amazing. Okay. Any other questions? I'm going to be very late with your assignments, okay? But I'm going to mark your assignments at one point. By May 20th, I'll mark your assignments. Any questions, guys? If there are no questions, thank you very much. And I'll see you on Friday.
Thank you, Ivo.
Stay safe.
Bye.
Thanks a lot.
Bye-bye.
Bye-bye.